So today we are going to discuss Burrows-Wheeler indexes. Let me motivate why these indexes are important for our current module, strings and exact matching. We closed the last lecture by discussing generalized suffix trees and applications of suffix trees. Right. So this was important in data structure, and we saw that how suffix trees are applicable to problems beyond just pattern matching. So for example, initially the suffix trees were invented for locating the occurrence of patterns in a large text, but subsequently their applications have grown. So we saw some applications in the last lecture that are non-trivial without suffix trees. So if you think of solving those problems without suffix trees, it would be harder, whereas suffix trees give a very simple and elegant solutions to those problems. So far we have looked at two important data structures, one is suffix array and one is suffix trees. So in both data structures we have to also consider the space that these data structures take, right. So for example, when we are constructing these data structures for large strings such as entire human genome or even longer genomes, how much space do these indexes take in memory? Because when we are doing any pattern matching or any other application, we will have to store these data structures in memory, right. So asymptotically we know that both of these data structures take linear space. So for example, I can even say that the input text of length n asymptotic. So if I want to store the input, it will take order n space. If I want to store suffix array, it will also take order n space, because all I am storing is n integers. In suffix trees we also proved that the space requirements of suffix trees are linear. So asymptotically all these three, the input text, suffix arrays, suffix trees, they all three take order n space. But what about the constants involved in order n, right? So in big O notation, remember that the big O notation hides the constants. So when we are dealing with large amount of data, we have to also worry about these constants, like what is the exact value of constant involved. So if constant is 1 versus constant is 10, that can make a huge difference in the practical applications of these data structures. So if we look at the exact bit count that we would use to store these, so for example, if I talk about storing the input text t, then because each character is over alphabet sigma, we know that we can use n log sigma bits and store that input text, right. So all I need is n log sigma bits to store the input text. For suffix array I need n log n bits, because each element of suffix array is an integer, right, and suffix array is a permutation of numbers ranging from 0 to n minus 1. So therefore to represent each integer I need log n bits, right. So that also we discussed in the previous lectures, that suffix array would take n log n bits. What about suffix trees? Well, one thing to observe that is suffix trees would take more space than suffix arrays, right. So remember that in suffix trees, if you just let's look at the leaves of the suffix tree. So just the leaves of the suffix trees are equivalent to the space used by suffix arrays, because we have n leaves in the suffix trees, and in each suffix if we store the id of the suffix, that is the starting position of the suffix, let us say 5, 3, some 2, for example as shown in the figure here. If we store these ids of the suffix, then the leaves themselves are taking n log n bits, right. Now but just leaves is not what the tree contains, right. The tree also contains internal nodes, the tree also contains edges. So for example, the internal nodes we know that the number of internal nodes is less than equal to n minus 1. So in at most they will take order n space, but in each internal node we will have to keep pointers of their children, right. So, saving those pointers is also going to take some amount of space. Similarly, you have edges in the suffix trees, right. So, you have edges in the suffix trees, on those edges also we have to store the information for edge labels, because on these edges we are keeping these string labels in the form of pointers, right. So, we discussed that instead of storing the exact label, all I need is a pointer in the text which will tell me what substring corresponds to that label. So, for example, for this I can store a pointer to the text saying that this text starts from here and has length, in this case 6. So, all this information like internal nodes, edges, leaves, this implies that the space requirement of suffix trees is greater than the space requirement of suffix arrays. So, what we can say is that suffix trees require more than n log n bits, and in practice if we look at the practical implementations, then we can say that the space used by suffix trees is some constant times n log n, and in most practical implementations that constant will vary from 3 to 5. So, starting from the input text which only used n log sigma bits, we increase the space requirements to n log n when we define suffix arrays, and for suffix trees we further increase to some constant times n log n, where that constant typically ranges from 3 to 5 in practical implementations. Now, why is this important? Like, why are we discussing this exact bit count? If we look at real data, for example, in this case I am taking an example of the recently assembled genome which is coming from the Australian lungfish. This genome is 43 billion base pair long. So, this is 14 times longer than the human genome, and if we look at the space used to store the input, that is the space used to store the genome itself, then it would take about 11 GB space to store the input. However, for suffix arrays it would take 193 GB, taking into account that we are using n log n bits, and for suffix trees the space requirement goes to 772 GB. So, this is assuming that the suffix tree implementation that we are using is requiring 4 times more space than the suffix array. So, you can see that why the space matters now, because if I want to develop a tool and that tool should be usable on general hardware like any laptop or any server, then 772 GB is too much space. We may not expect that everyone has access to systems which has 772 GB RAM, right. So, in fact, very few people will have access to RAM that exceeds 772 GB. So, therefore, looking for space efficient data structures is very important, and I have emphasized that before as well. Moreover, there are even longer genomes. So, Australian lungfish is not the largest genome. So, there is another example like Paris japonica. This is a native plant of Japan, and in this case the genome length is 150 billion bases. So, now you can imagine that the suffix trees and suffix arrays would take even longer space for these longer genome. So, the motivation for this lecture is to look at another index data structure, that is known as Burrows-Wheeler index. This is going to be a space efficient version of suffix arrays and suffix trees, in the sense that we will try to show that this data structure is powerful enough to support the applications of suffix arrays and suffix trees, yet the space requirements of Burrows-Wheeler index is going to be significantly smaller. So, it is going to be using only n log sigma 1 plus small o 1 space. So, that is the space used by the text itself plus another small amount of space for storing additional index. So therefore this comes into the category of succinct data structure. So you can see that the space requirement here is almost matching the space required by the input text. It is significantly smaller than the space required by suffix array and suffix tree. So this data structure is also part of commonly used tools in bioinformatics. I am showing you one example on the bottom left corner. This is a commonly used read mapper, and you can see that it has been cited more than 40,000 times. So you can see the impact of the topic that we are going to study today is this Burrows-Wheeler index allows space efficient indexing of large genomes, and that forms the basis of many tools being used today in bioinformatics. Okay, so this is going to be the agenda of this lecture. First we will start with the data compression techniques, and the data compression technique will be the Burrows-Wheeler transform. We will look at this data compression technique because this forms the basis of the index that we are going to study later. So the index that we are going to study is motivated from the compression technique that was proposed few decades back. So here is the timeline of the inventions as far as these topics are concerned. So this Burrows and Wheeler text compression was invented in 1994, and as you can see, the Burrows-Wheeler transform takes its names from the authors who invented this technique. Later, a decade later, it was realized that this compression mechanism can also be used as an index, in the sense that if we make some modifications to this compression, then we can also do fast information retrieval while using small amount of space for the index. And few years later, it was realized that this indexing technique can be very practically useful for genomics applications. So therefore many tools and software such as BWA, Botai, SOAP2, they adopted this technique, and people benefited from this algorithm on a day-to-day basis. So the flow of this lecture is going to be that we are going to study this compression technique first, and then we are going to see how this compression technique extends to indexing data structure that also permits fast information retrieval. So by indexing, I mean that it should support the information retrieval, that is the applications that we discussed with suffix arrays and suffix trees that allowed fast pattern matching. So we will see in the subsequent phase how this compression technique is useful for fast pattern matching as well. So let us look at the data compression technique that is known as Burrows-Wheeler transform. So the Burrows-Wheeler transform at a high level, so it takes the text T and it just permutes the characters of the text T. So for example, if you have text T A B A B A dollar, then what Burrows-Wheeler transform would do is it will permute the characters of this text. So it will shuffle the characters of this text in some way. We will discuss how exactly that permutation is achieved in the next slides. So to see how Burrows-Wheeler transform permutes the characters, let us understand it in the following way. Let us take the text T as an example. So this is example A B A dollar. Let us consider all cyclic rotations of this text. For example, one rotation is the text itself. Then the next rotation I will rotate this text by 1 cyclically. So the dollar symbol moves on the left by 1 position. So this is a cyclic rotation and A comes forward. Similarly, in the next rotation the dollar symbol moves further on the left, and we can similarly enumerate all cyclic rotations of this text. So if this text is of size 7, then we have 7 distinct cyclic rotations of this text. So once we consider all the cyclic rotations, as a next step we are going to sort these rotations. So we are going to lexicographically sort these rotations, and because we continue to assume that the dollar symbol is lexicographically smaller than A and B, naturally this rotation starting from the dollar character appears at the top, followed by rotation starting from A character, followed by rotations starting from B character. But wait a minute, does this remind you of anything? Observe that this is very similar to the suffix arrays that we have already seen. So, this, if you look at this blue text here, this is a representation of the suffix array, because you can think of them as suffixes and these are sorted suffixes in some way, if you only look at the blue text here. Okay. So, once we have sorted all the cyclic rotations, Burrows-Wheeler transform is nothing but the last column of this matrix. So, the Burrows-Wheeler transform of text T is basically A, B, B, A, dollar, A, A. That is it. So, we compute all the cyclic rotations, we lexicographically sort them, and then we look at the last column, and that is your Burrows-Wheeler transform of the text. So, that is a very extremely simple definition. So, you take the cyclic rotations, sort and take the last column. We can also define Burrows-Wheeler transform in terms of suffix array, because we see there is a connection with suffix arrays as well. So, observe that the ith character of Burrows-Wheeler transform equals the character that precedes the ith character in the sorted order. So, for example, the first character of Burrows-Wheeler transform is the character that precedes the dollar suffix, because dollar suffix is the first suffix in the sorted order. So, the character that precedes dollar suffix is A. So, therefore, the first character of my Burrows-Wheeler transform is A. Now, the next suffix in the sorted order is A dollar. Similarly, if you look at the A dollar string, the character that precedes A dollar string is B. So, therefore, the next character of my Burrows-Wheeler transform is B. So, I can generalize this by saying that the ith character of Burrows-Wheeler transform is the character that precedes the ith suffix in the sorted order, right. And if the, so if this SAI is 0, that is for the very first so that is for the very first so that is when the text corresponds to entire string, right. So, SA 0 means that you are talking about the suffix that represents the entire string, then in that case your suffix, the Burrows-Wheeler transform character will be dollar, because in that case, in the case where the suffix corresponds to the entire string, in that case your Burrows-Wheeler transform character will be dollar symbol. So, that is what this formula is representing. So, therefore, there are two ways of defining Burrows-Wheeler transform. One is in terms of the cyclic rotations, and second way is in terms of the suffix array. So, suffix array gives you a more precise way of defining the Burrows-Wheeler transform. So, at this point I hope the definition of this transformation is clear, but we have to answer now three questions. Why is Burrows-Wheeler transform useful for text compression? Because this was the original motivation for building Burrows-Wheeler transform. So, in 1994 Burrows and Wheeler invented this technique for text compression. So, this has to be useful for compression, but that is why is the reason, like it is not obvious at this point. Second is, if this is a compression technique, then there must be a way of going from Burrows-Wheeler transform back to the original text. So, this is a lossless compression technique, which means that there must be some way of taking Burrows-Wheeler transform as input and going back to the original text. Finally, we will see how this compression is going to be useful for indexing the text. So, how does it support the functionalities of suffix array or suffix trees? Because we only have access to this column, and how can this column alone support the functionalities that we saw with suffix arrays or suffix trees? So, that also we will see. So, let us start with the first question: why is Burrows-Wheeler transform useful for text compression? To see this, let us consider an example, right. So, let us download the paper written by Burrows and Wheeler. So, this was a paper written in 1994, and for that paper itself, let us compute the Burrows-Wheeler transform of that text. So, if you open this PDF, you will see that the document describes this algorithm. But what if we compute the Burrows-Wheeler transform of that paper itself? Let us do that. And so, once we do that, what we will observe is, so in this figure I am showing you the Burrows-Wheeler transform represented by this column in orange. To compute the Burrows-Wheeler transform, remember that we have to sort all the suffixes in that document, and once we have the sorted suffixes, we will look at the characters that precede the sorted suffixes. Now, remember that when we sort the suffixes, as an example, all the suffixes that start with n symbol. So, I am only showing you a subset of suffixes here. I cannot show you all the suffixes because there will be too many. So, the suffixes that start from n characters are following. So, for example, you can see n to decompress, it achieves compression, n to perform only comparisons to the depth. So, this looks like a text coming from a publication, right, and in fact you can verify by opening the paper itself. Now, if you observe the character that precedes this n symbol, you can intuitively expect that when I am writing English documents, the character that precedes n symbol is very likely to be a vowel symbol, because normally when we are writing English documents, all the words which involve n, most likely they will be preceded by a vowel symbol, and as a result what you see is that similar characters tend to repeat in the Burrows-Wheeler transform. So, for example, if you have a suffixes starting from n transformation, it is very likely that they will be preceded by o, because it makes sense that on transformation, right. It cannot be and transformation, it has to be on transformation. So, therefore, similar suffixes will be preceded by equal letters in the Burrows-Wheeler transform, and because of this repetition, it is easy to compress the string that has runs of repeated characters, because once you have these runs of repeated characters, instead of writing them as a o o o o, I can write it as a followed by 4 o symbols, followed by 2 a symbols, followed by 2 I symbols, and so on. So, I can write the distinct characters and their counts in the run length encoding technique. So, this is why Burrows-Wheeler transform helps in compression, because it brings the equal letters together when we build the Burrows-Wheeler transform. Let us look at one more example, and this time let us look at the text kabaddi, 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 kabaddi. In this case, let us try to understand where will the k characters go in the Burrows-Wheeler transform text T. What do you think? Well, observe that the ordering of k characters will be determined by the suffixes that occur next to k characters. So, these are the suffixes starting from a b a a d I. So, this one, then the next suffix is this, the next suffix is starting from again a b characters, and the next suffix starting from here. Now, because all these suffixes start from a b letters, you can imagine that once I sort the suffixes, these suffixes are going to occur next to each other, and as a result the characters k will come together in the Burrows-Wheeler transform, because Burrows-Wheeler transform is nothing but the characters preceding the sorted suffixes. So, if you look at the Burrows-Wheeler transform of this example, you can see that all the k characters occur next to each other, and similarly for all other characters again you can see that many other characters occur next to each other, and this Burrows-Wheeler transform looks extremely repetitive and we can easily compress this string now. So, it is harder to compress the original text t, but this particular text looks very compressible. So, this again I can represent as run length encoding using run length encoding. So, for example, I can say that the underscore symbol occurs 2 times, I symbol occurs 4 times, k symbol occurs 4 times, and so on. In fact, in the terminology I can say that this is one run of Burrows-Wheeler transform, this is second run of Burrows-Wheeler transform, this is third run of character k, similarly this is fourth run of character b, fifth run of character a, sixth, seventh and eighth run. So, this text has 8 runs in the Burrows-Wheeler transform, and the first run is of length 2, second run is of length 4, third run is of length 4 and so on. In this particular example, the average run length is 4.12. So, that is just the average of all the lengths and reporting this number. Okay. So far we have looked at either the English document or this example kabaddi, 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 right. What about biological examples? So, here is one. If you build Burrows-Wheeler transform of the human genome, so for example, let us say we take one human genome and we build its Burrows-Wheeler transform, then one human genome, if you count both father's and mother's copy of the genome, then it will be 6 billion bases. So, here M stands for million, and the number of Burrows-Wheeler transform in this for this particular text will have about 3 billion runs. So, I am showing you in millions here. So, this is the number of runs in the Burrows-Wheeler transform. But now suppose you take 2 human genomes and build a longer text, then the text will grow to twice its size approximately, right. But observe that the Burrows-Wheeler transform grows very slowly because of the characteristics that for repetitive text it is significantly more compressible. Similarly, I take 3 genomes, the text size grows linearly, but the Burrows-Wheeler transform, the number of runs in the Burrows-Wheeler transform grows very slowly. So, this is a real world example where you can see that the text size grows linearly, but the number of BWT runs are growing very slowly. So, therefore, if you want to let us say index 10 or 20 human genomes, Burrows-Wheeler transform is a very nice technique to compress the text. So, if you store it uncompressed, then the space utilization will grow linearly very fast, but if you use the Burrows-Wheeler transform compression, then the space utilization will grow very slowly. So, this shows you an example of why Burrows-Wheeler transform is powerful as a text compression technique. Also, I want to mention that if you are using any Linux, Mac OS or Windows systems, then most operating systems will already have this tool bzip2 installed on the operating system. So, for example, if you have a Linux system, you can go and try compressing your file, and you will see that it will produce a compressed file at the once you run this command. That file will have extension bz2. If you open the man page of this tool, you will find that it will describe the algorithm behind this tool, and it will there you will see that the algorithm being used underneath is based on Burrows-Wheeler transform that we just discussed now. So, the technique that we discussed just now is not just relevant for biological sequences, but it applies to general text compression as well. So, you can compress even image files or any sort of large document that you may have or large folder that you may have, right. So, this is a general compression technique that was developed by Burrows and Wheeler. So, we understand by now that why is Burrows-Wheeler transform useful for compression. I still have to convince you that this is a lossless compression technique, and by which I mean that there is a way or there exists an algorithm that will take Burrows-Wheeler transform as input and you can get back your original text, because that is the algorithm that will be used if you, for example, want to decompress back from your compressed file and recover your original file. So, that algorithm we still have to discuss what technique we can use from going back to the original text from the Burrows-Wheeler transform. So, let us look at this technique of taking Burrows-Wheeler transform and recovering the original text back in the next lecture.